processes now influence the isotopic composition of water when it's in an organism. And I'm going to talk about my favorite organisms, which are plants, but I have to recognize that there are other organisms like elephants, and those are supposed to be microbes, butterflies, and birds. So if you look at the isotopic composition of those organisms, what are the principal rules that apply to everybody? So I don't want to focus so much on individual examples, but to make sure you understand the fundamentals. Because once you understand the fundamentals, I'm a big fan of if you know the rule, you can make the prediction. But if you don't understand the rules, you can't. So the environmental water that comes in can be in the form of precipitation. It could be evaporated water. It could be stored water. Whatever it is, it's coming into the organism. And we've established that, for the most part, and I'll say completely, that there's no fractionation during uptake. Now what happens into the organism when we get organismal water? We see a very consistent pattern that the pools of water within an organism can be very structured. The pools of water in your body are structured. If you happen to be a cancer patient, the pools of water within your body are very exaggerated. And that's because we need to consider two processes: evaporation. I'm evaporating water right now, and I'm actually not evaporating water, which is exactly the same as my body water. There's a fractionation during evaporation. No fractionation during my consumption, but a fractionation during evaporation. So we need to consider that. And then we need to recognize something we haven't talked about before, and that's metabolism. Metabolic water. If I take a carbohydrate I'm going to get water generated. And I'll just give you a hint, because you haven't heard John's lecture yet. The isotopic composition of most of the food that you eat, or that animals eat, are between plus 25 to plus 35. Dude, they are very isotopically enriched relative to body water. If plants are taking up water which is minus 15 to minus 5, and you're drinking water which is, let's say, minus 15 to minus 5, and now we have metabolic water which is produced, which is starting off with a carbohydrate that's plus 27. Even if it doesn't all end up in water, a significant fraction will. And that raises the isotopic composition of body water. So metabolism raises the isotopic composition of body water. Now, I know Marin is going to say, well, that might be true, Jim, that we have lots of metabolism in these cells and they increase the isotopic composition of water, but so what? That water is leaking out of the plants. I mean, it's leaking out of the cell and into the rest of the body. I'm going to say, not so fast, Marin. Recognize that for that water to get out, you need an aquaporin. And so if you have lots of aquaporins, then of course there might not be much of a gradient. But imagine a situation where you have very few aquaporins and you have a high rate of metabolism. You could end up with the body water in a cell which is isotopically distinct from other parts of the body. I'm not going to say that is the case, but you must accept the fact that that case could be. So that we have these pools, these two processes, metabolic isolation and evaporation, that can change the isotopic composition of water in a microbe, in a leaf, in a root, in an elephant, in a cancer patient. Then we want to transform that water. We want to know how that isotopic composition of water is going to get recorded. I want to have that recorded. I want to know something about what that leaf water was, because as much as I love Sergey, I'm not going to be a slave to him and sit in the lab and measure the isotopic composition of those cells every single minute for every single day. I want isotopes every day. And they will. So here's our general model. And I present this conceptually and tell you that this model can be applied to every living organism on this planet. So we have water, which is taken up. We have water, which is transported from its region of uptake to other parts. And we have regions in which water is lost. So to use this as an example, this might be my gut for taking up water. It might be my lungs or urination for losing water. It might be my muscles for organs. And it might be my veins for how that water is transported. Now, you want to be able to measure the isotopic composition rather routinely. And I'll tell you, the simplest way that I can measure your body water right now, what's the simplest way I would measure the isotopic composition of your body water? Breath? No. Huh? Urine. That's it. There's no indication that there's any isotopic composition difference between the isotope ratio of water in veins and urine. And I'll tell you one of the cool things. We did this about 5, 6, 7 years ago. You can take this wonderful instrument that you'll see called the Picaro, and I can just take urine directly and shoot it into the Picaro. And we have done this. Okay, it clogs up the filters after a while. There's no reason to clean it up. So we've measured the body water of hundreds of people just by measuring the isotopic composition of their urine. Because we wanted to be able to work back and understand a number of these processes. So let's take this general model and let's begin to give you some specific examples. Well, I'm a botanist, so plants take up water through the roots, it goes into the xylem and phloem, it gets stored in a tissue, which might be a flower, might be a root or a seed, it comes to the leaf. Oh, the leaf is analogous to the lung. The leaf is the place in which that water is going to be isotopically enriched because it interacts with the environment. And now, Maria here is going to say, gee, Jim, I already know the rules for leaf water. Because I heard Turi and I heard Gabe tell me about this thing called Craig Gordon. I'll say, oh yeah, you are exactly right. If you know Craig Gordon, you can predict exactly what the isotopic composition of leaf water should be at equilibrium. I can apply the same thing to a vertebrate, in which case we now have a blood system. We don't have xylem and phloem, we simply have a single blood system. And then we have a tissue and organ, and then we have a lung. Or I might apply this to an insect, in which case I might have a spiracle. I can apply this to a microbe, but if it's unicellular, in theory, there's just going to be one pool. And I'm going to tell you that if you take that concept, you know that you can have access to every model and equation that allows you to make a prediction. So I can predict what the isotopic composition of a butterfly is going to be over time. I can predict what the isotopic composition of a spider will be, of a human, of a cell. And if I recognize that metabolism is an important part, then I might actually be able to use that as a piece of information. So, for plants, we have evaporation models. The one model you haven't heard about so far is the string of lakes. How many of you have heard of string of lakes? 1, 2, 3. Okay. So the string of lakes is a very simple concept. It was first developed by Joel Gatt. So often you hear about this in Turi's lecture or in Gabe's lecture. So the string of lakes is a concept in which we have one pool of water which comes into the root. But imagine that that water has now come into a lake, and as leaving that lake, it's going into another lake. It's leaving a second lake and going into a third lake. Well, the input water into lake number 2 is not the same as the input water into lake number 1. The input water into lake number 3 is not the same as 2. It's not the same as 1. So in the string of lakes, you need to recognize that the particular part of the organism you're looking at is influenced by something else, not the original source. And the easiest example to think of beyond a string of lakes is a grass blade. So the base of the grass blade will reflect the water which has come in from the root. But as you move along the grass blade, farther up is influenced by the leaf water down below. Farther up is influenced by the leaf down below. So you have a progressive difference in the isotopic composition in lakes and a variation in the isotopic composition in a leaf that's a grass, but not blue leaves. So you can take this concept, and if you recognize string of lakes, and you recognize Craig Gordon, you have all the models you need to predict for plants. We have these models available for you as equations, as Excel spreadsheets, and so forth, so they're available. We have body water models. There's a whole literature out there of body water models that allow you to predict how, on average, the isotopic composition of an organism, usually an animal, vertebrate, will change with environment, with metabolism, with environment, with breeding relationships. So these models all exist. So they take advantage now of evaporation processes that are known and of metabolic isolation. And metabolic isolation is the most exciting thing that I think has come out in the last 5 to 10 years. And I'll give you the take-home story. Take-home story is that if you have lots of metabolism, you have lots of metabolic water. If you have lots of metabolic water, that water is going to be very different than the water that came in. So a cell that has a high rate of metabolism should have a different water isotope ratio than a cell that has a low rate of metabolism. Fair enough? Now, you start to think about this when I'm interested in applications. Well, I don't know of any cells in plants that have a very high metabolic rate. There might be a few sometimes, but in general, no. Animal systems? Well, it depends. Depends on whether or not the system is diseased. Oh, let me think of a particular disease called cancer, in which you have a high metabolic rate. I have potential to isolate that cell and determine whether or not that high metabolism cell is a different isotopic composition. Or I might take something even simpler. I might take a microbe which is in log phase growth, or a microbe which is in sporulation phase, which has a slower rate of metabolism. So those body waters are going to be different. What Sergio wants me to take advantage of is, gee, Jim, I don't really want you spending all your time measuring the isotopic composition of that water. Why don't you find a protein that's being made in the cell during this event? And maybe the hydrogen and oxygen isotope ratios of that protein will reflect that metabolism. It is in fact the case. So these models exist. The literature is well established. We can first start off with the plant example of leaf water enrichment, in which we have water that comes in, water gets into this middle part here, in the air spaces where the humidity is 100%, and then leaves. Oh, that sounds an awful lot like what Keeling spoke about. So, because the lighter isotopes are leaving differently than the heavy isotopes, we have leaf water which is enriched. Leaf water is always going to be enriched, and the degree of enrichment is going to depend on the humidity. Just like the deviation from the New York water line was different from the Amazon River than it was from the Rio Grande. That's very predictable. And of course, the model that I'm going to use is the Craig Gordon model. It's the same model. So I won't spend much time on it, but it's the same model. So, I want to give you, yes?
Can you talk about the Peckley effect?
No. Can I? Yes. But let's see if I make it through the next 10 minutes.
I'll refer to it a bit, but not.
Okay, John will refer to it. Not
not
everybody
actually.
believes in the Peckley effect. Not everyone accepts that the Peckley effect exists. The Peclet effect cannot be tested independently.
Yes.
Can it?
No.
No. So it cannot be tested. So it's a concept that can exist. And had I not known about aquaporons, I could have said, yeah, there could be creeps for the Peclet effect. But I think there might be other ways of explaining this. So I would say the Peclet effect is an area of active engagement, and let's let John talk about it. So what I do want to say is that we can grow microbes. When Helen was in the lab, we used to grow a lot of cellulose, which is an endospore. It's a soil microbe. It's not toxic. And we would grow them in a certain media. And then we would get cake solutions, which is basically we would take the microbe out of its matrix, and we would measure the isotopic composition of the microbe. And I'll be damned. The isotopic composition, I'll be darned, sorry. The isotopic composition of water in the medium was never the same as the isotopic composition of water in the cell. So either one of two things is happening. Either there's a fractionation during uptake, or something else is influencing the water. What Helen showed was that it was the water metabolism. So the slope here was not a slope of 1, but the slope was about 0.9. So something was going on to suggest that the water inside these cells that were metabolically active was different. And she went on to show that if you had these bacteria in the log phase growth, where they're very rapidly dividing, or when they were sporulating, so they weren't dividing so fast and metabolism was slower, that the amount of water change was different. That the biggest difference occurred in the log phase growth. So, any questions on this general concept that we can have compartments of water within an organism? Yes, Maria.
So if metabolic rate alters the isotopic composition, then it might be best in plants to take samples only from xylem and not from roots, because tip roots can be metabolic. Yeah? Okay.
So that what Maria has just said is that if metabolism is affecting things, maybe it's best for it to take water from the roots and not the leaves, or vice versa.
Yeah.
And I'm going to respond with what I think is the observation that Helen and others have observed. The general rate of metabolism in plant cells of all types is so slow that we never see any metabolic water gradients at all. So this is a phenomenon that we've only been able to document in vertebrates and in microbes. This was started with the paper that Helen Kreuzer had in the lab in PNAS probably 15, 20 years ago, and it's blossomed into a whole separate literature, so I haven't kept up in the last couple of years.